welcome to my presentation. My name is Jui Keskar, and I'm honored to present here today. The title of my research is JChaosIndex, Measuring and Benchmarking Dispersion in Randomized Data. So just a little background about me. I'm a high school student at Metropolitan School Frankfurt in Germany, and this research focuses on a novel metric that I have developed to measure data dispersion, which has applications in fields like AI, clinical trials, and gaming. So I'll start. So randomization is essential in many areas. For example, say in clinical trials, it ensures fairness by distributing participants evenly across test groups. And in AI, randomization helps create unbiased training datasets, and which can further improve the efficiency performance of the model. In gaming, it ensures that outcomes are unpredictable and fair. So in all these scenarios, we cannot know just how random each data is, or if one data is more random than the other. And for us to be able to control its randomness and dispersion, we first need to measure these, which is something we face a challenge doing. While tools like random number generators in programming languages do exist, they lack a systematic way to evaluate how well data has been randomized. And this is the gap. This is the gap my research aims to address with JChaosIndex, which is a technique to measure dispersion. Dispersion tells us how much the data has been shuffled, which is key to understanding the quality of randomization. Dispersion, in other words, tells us how far each data point has moved during the randomization process. And it also tells us how far the neighbors of data points, the immediate, like after or before, have moved away from their original position. So, yeah. So my work delves into three main objectives. Firstly, to develop a metric called JChaosIndex that can measure the dispersion in randomized data, like I mentioned. Dispersion is an important factor because it provides insights into how well the data has been mixed. Second, I ensure that JChaosIndex is domain and data agnostic, meaning that it can be used across various industries and for different types of data. So this means that it could be used across, say whether it's for medical records or financial data or gaming logs, and more data like that. Lastly, I also benchmark this metric against randomization techniques commonly used in programming languages like Python and C#, to name a few, and to see how well it performs in real-world scenarios. So to understand why this research will bring value, let's look at the current state of the field. Right now, tools like permutation entropy, which I'll come back to again, are used to measure unpredictability, which is one aspect of randomization. However, they don't measure the dispersion, which is the physical spreading or displacement of data points. Dispersion is critical because it evaluates whether the randomization has adequately shuffled the data. And my work combines these two aspects, unpredictability and dispersion, for a more comprehensive analysis. So here's an overview of how JChaosIndex works. First, we measure how far each data element has moved from its original position after randomization. This is called absolute displacement. Second, we look at how the relative positions of neighboring data points have changed. For instance, if two data points were close together before randomization, how far apart are they now? Finally, we normalize, I normalize these values by the data set size to, normalization. It ensures that the metric is consistent and comparable across data sets of different sizes as well, so that size does not affect the, By combining absolute and relative displacement, JChaosIndex gives us a comprehensive view of data dispersion. For example, in the chart, we can see the original data point on the left and the randomized data points on the right. So ID1 is the original and ID2 is the, sorry, my bad, the other way around. Um, and um, as we can see in the third data point in the randomized data has displaced by one position upwards, and its original neighbor, which was the second data point, has displaced by two positions downwards in the randomized data. So my point here is that all such displacements are taken into account in the JChaosIndex while measuring the total dispersion of data. So this slide showcases the formula for JChaosIndex. So it looks kind of complex, but I'll break it down. The formula measures two things: the absolute displacement of each data element and the relative displacement of its neighbors. The function named old, as we can see here, takes the new position of the data element as its argument and retrieves the original position of the data point. And the new function takes the old position as the argument and retrieves its randomized position. The first summation sign is for the data element, and the second summation sign is for the relative position of position change for every neighbor. These values are then summed and then normalized by as you can see here, 1 upon n square, which is the square of the data set size. Normalization here ensures that this metric remains consistent regardless of how large or small the data set is. A higher JChaosIndex indicates greater dispersion, meaning that the data has been well randomized. So here, as you can see, like ID2 and ID1, they are connected to this. ID1 is this column and ID2 is this. Yeah. So before we dive any deeper into this, I'll briefly talk about permutation entropy. So this is a metric that is used to measure unpredictability by analyzing the order of values in a data set. It's particularly useful for time series data where the sequence of the values is critical, such as say stock prices or some sensors readings. In my work, I use this because it helps identify the most unpredictable configurations. Once these are identified, JChaosIndex then can measure how dispersed these configurations are. And this combination of the maximum permutation entropy and maximum data dispersion using JChaosIndex will provide a more complete picture of the data randomization. Also, I'll skip this formula for now because it's not something I developed. So now I'll talk a little bit about the implementation. So we can start by preparing both the original data set and the randomized version by randomizing the original data set. Then calculate the absolute and relative displacements of each data point. These values are then normalized to compute the JChaosIndex. I used programming languages like Python, Java, C, and C# for implementation and benchmarking. Each language offers different randomization techniques. So benchmarking across them allowed me to test the robustness of JChaosIndex. For example, trying it on Python generated highly dispersed configurations, while C# struck a balance between unpredictability and dispersion. This code is a tiny snippet from the snippet that calculates the total displacement needed for calculating the JChaos index, but the complete code is in the paper. So these are the results of my analysis that show that the maximum index here trends linearly, as we can see, with the dataset size, my bad. This means that as the dataset grows, the metric changes, metric scales predictably, which is a key advantage. It also confirms that JChaos index provides an objective measure of randomization quality. For example, in small data sets, even slight changes in dispersion are noticeable, whereas in larger data sets, the metric remains consistent and reliable. Um, the dataset size chosen here, as you can see, are quite small because bigger data sets will require an insane amount of computing power since there are a lot of calculations involved. However, the trend depicted by these 10 elements is so robust that it is enough to estimate that this formula will work for all sizes. So now let's look at the most dispersed configurations. So these configurations maximize the displacement of the data points, which sounds ideal. However, it does have a downside because such configurations can be predictable. For instance, if the randomized data is simply a reversed version of the original data set, it's not truly random. It's predictable, but it still has the maximum dispersion. And what I try to do is I try to find the optimal dispersion. So by combining dispersion with permutation entropy, we can identify configurations that are both dispersed and unpredictable, making them useful for real world applications. Yeah. So so the slide shows the distribution of permutation entropy and JChaos index across different permutations of the data and data set sizes. So as you can see, data sets with high permutation entropy also tend to have a higher JChaos index, but there are exceptions. Oops, sorry, I meant to, yeah, this one shows that better. So here we can see that as you can see, the data sets with higher permutation entropy here. Um, the graph I've plotted is permutation entropy against JChaos index, and the data sets with higher permutation entropy also tend to have a slightly higher JChaos index. As you can see, there are more. It is more heavy on this side. Um, but there are exceptions for sure, and these insights help us identify configurations that strike the right balance between unpredictability and dispersion by giving a constraint for uh, how much dispersion we want, how much max dispersion we want. So for example, here we can see I point out the area of interest here because this is the point where the permutation entropy and JChaos index are both the highest, which is what we're going for. So to benchmark these randomization techniques, I tested JChaos index across different programming languages, like I mentioned, Python, Java, C, and C Sharp. Each language has its own randomization library, and the results were kind of fascinating. Python generated the most dispersed configurations, while C Sharp offered a good balance between unpredictability and um, dispersion. This shows that the choice of programming language can significantly impact the quality of the randomization that we're looking for. So Now, coming to the application of this, JChaosIndex can have diverse applications in, say, for example, AI. It can help prepare data sets that are free of bias, improving the model's accuracy, and it can also improve the implementation of the 80/20 rule. In clinical trials, it ensures fair participant allocation, which is critical to get unbiased results. And in gaming, it reduces predictability, making games more engaging. So, looking ahead, I plan to integrate JChaos Index into randomization libraries. Of course, I haven't done that yet, but this will make it easier for developers to use this metric. Yeah. So, to sum up, JChaos Index is a robust domain-agnostic uh, metric for measuring the data dispersion. It benchmarks well against existing techniques and addresses key challenges in randomization, such as balancing dispersion and unpredictability. And I hope that this research will inspire further exploration into randomization. So, yeah, I'd like to thank my parents, my mentors, and my school for supporting me throughout this process. And I would like to thank this conference for giving me the opportunity to put forward this research. So, yeah, thank you.